with something like, let's start with something that we've probably done before, and that's H2O. Okay? What's the first thing you do if you're trying to do the Lewis dot structure of something? Valence shell electrons. Okay, so hydrogen has how many valence shell electrons? 1, okay, and there's 2 of them. And oxygen has how many valence shell electrons? 6. And how do we know that? How do we determine the valence shell electrons? Yeah, you look at the periodic chart and see what group number it's in, because the group number tells us the number of valence shell electrons. So we have 8 valence shell electrons. Okay, so now what do? We've got our total valence shell electrons. Next thing we do is figure out the central atom, right? Okay, so which one's going to be the central atom, hydrogen or oxygen? Oxygen. Okay, it's never going to be hydrogen. Okay, so oxygen's our central atom, and then we draw our skeleton. All right, and then by doing these lines, that takes care of 4 electrons, so we have 4 electrons left over. So where do the leftover electrons go? Around the oxygen. Normally we would put them around the terminal atoms to satisfy the octet, right? So why can't we do that with hydrogen? Yeah, it can only have 2, and that constitutes 2. Okay? So then we would put lone pair electrons around the oxygen. Okay? So that would be the Lewis dot structure of water. All right, so let's do something like sulfur hexafluoride, or SF6, sulfur hexafluoride. So in that particular case, we start with valence shell electrons. How many valence shell electrons does sulfur bring? 6. And fluorine? 7 valence shell electrons. There's 6 of them. What's 7 times 6? 42. 42 and 6 is 48. These are the most common mistakes that are made. It's right here in the little math part. Because we get excited and go ahead and add incorrectly or something crazy. So take your time and do your math correctly, because that'll affect how you're going to draw your structure. So what's your central atom, sulfur or fluorine? Sulfur. Okay, why sulfur and not fluorine? Okay, so we have extra number of fluorines. This would be one clue. And then the other thing is sulfur is the least electronegative. Okay, so sulfur goes in the center. Okay, each one of these lines represents 2 electrons. That's a bonding pair of electrons. All right, so by doing this, we've taken care of 2, 4, 6, 8, 10, 12 total electrons. We have a few left over, don't we? And where do those leftover electrons go? Going to go around fluorine to satisfy the octet, right? Because fluorine is one of those atoms that will satisfy the octet rule. It will have 8 electrons around it. So we put them as lone pairs around the fluorines to satisfy the octet. Notice how we're putting them as pairs and not just random dots. Okay? They go as pairs. All right, and then we count up the total number of electrons that we have. 2, 4, 6, 8 around each fluorine. And how many fluorines do we have? 1, 2, 3, 4, 5, 6. So 6 times 8 is? Ta-da! Are you comfortable with that structure? Is everybody okay that there's 2, 4, 6, 8, 10, 12 electrons around sulfur? Oh my goodness, that's a lot of electrons, isn't it? How many do we normally have around the central atom? 8. But sulfur, since it's in period 3, can have more than 8 electrons around it. It's what we call an expanded octet. Okay, so it can have more than the 8 electrons around it. So that is a valid structure. Okay. Now, if you have any questions, you have to ask. Otherwise, I assume you're feeling good about this. Okay? Okay, so let's do boron trifluoride. First thing we want to do is count valence shell electrons. Boron brings 3. Fluorine brings 7. And there's 3 of them. So that's a total of 24 electrons. Okay, 24 electrons. So what's the next step? Central atom. What's going to go in the center? Fluorine or boron? Boron, because it's the least electronegative. Okay, so there's your skeletal structure. By doing this, we've taken care of 2, 4, 6 electrons, but we need to take care of more than that. So what happens to all the extra electrons? The fluorines, the terminal atoms, to satisfy the octet. And we place them as lone pair electrons. Okay? So now each fluorine feels as if it has 8 electrons. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So how many electrons do we take care of? 24. All right, are you comfortable with that structure? Is everybody okay with the fact that boron has 2, 4, 6 electrons around it? It's going to want 8, but remember boron, what period is boron in? Okay, it's in the second period, and what group is it in? Group 3. Okay, so boron is one of those that can actually have less than 8 electrons around it. It's okay with having 6 electrons around it. If we do it the old-fashioned way, boron has 3 valence shell electrons, and fluorine has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It kind of makes a little more sense that boron is okay with having just the 6 electrons around it. All right? Now, since the boron only has 6 electrons, it could have a place to accept some electrons and form another bond there. All right? When you get into 2045, we'll take that one step further and look at some of those structures as well. Okay? But right here, things that are in period 2, group 3, which would be boron, period 2, group 3 would be boron, is okay with having just the 6 electrons around it. It's satisfied in that sense. All right? Okay, let's do maybe one more, or a couple more. Do y'all need to do a couple more, or are y'all good? A couple more? Okay. All right, let's look at pH 3. Okay, pH 3. What's your central atom? Phosphorus. That one's kind of quick to figure out because we know it's not going to be hydrogen. Okay, hydrogen's not ever going to be in the center. So phosphorus brings 5. How do I know phosphorus brings 5 electrons? It's in group 5. Okay. Hydrogen brings 1. There's 3 of them. So that's a total of 8 electrons that have to be placed. All right. Now the way that we've drawn the skeleton, we've taken care of 2, 4, 6 electrons. So where do the next 2 go? On the phosphorus as a lone pair of electrons. Okay? All right, as a lone pair of electrons. What does this also look familiar with? What else can we compare this to? NH3, okay? Why can we compare it quite easily with NH3, with ammonia? Where is nitrogen on the periodic chart? It's the same group, isn't it? Okay, so